bondings are only two types. They are ionic and covalent bonds. But today's topic is intermediate bonding, which means in between ionic and covalent bondings. And we'd get substances having both ionic properties and covalent properties because they would have both type of bonding. So this we call intermediate bonding. And when we study intermediate bonding, then we'll get how an ionic compound gets some covalency or covalent properties, and how a covalent substance gets some ionic properties or ionic bonding. So we'll start from how a covalent substance gains ionic characters. Ionic characters are mainly because of charges of the ions. So they should have charges or they are ions. In covalent substance, we normally don't think to have charges or ions, and we say they are group of atoms covalently bonded and they are molecules. But they have charges, slightly charges. This we explain in terms of electronegativity. So a term very important, electronegativity. This is actually synonymous with covalent bond. A covalent bond is a general definition, which is the electrostatic attraction between the shared pair of electrons and nuclei of the atom. When you call this generally, this is covalent bond, and when you call this specifically, then this is electronegativity. What does it mean? Every atom of different elements will have different attractive force for the shared pair of electrons. Why so? Because they would have different nuclear charges. Nuclear charges depends on how many protons there are in the nucleus, and that the number different in different elements. So when they will make covalent bond, then they will attract the shared electron differently. There is another reason, you already got this, that size also matters. If an atom is big, then its shared electron is far away from its nucleus, so that would have less attraction for the shared pair of electrons. So what we get, the degree of covalent bond or the strength of covalent bond is different for different atoms for two reasons. One is for their nuclear charge is different, another is for their sizes. For both reasons we get this. And when you think about particular atoms, suppose hydrogen and chlorine, then what you get here, chlorine having nuclear charge plus 17, and I show here nuclear charge plus 17, and if this makes a bond with hydrogen, hydrogen having just one proton, so nuclear charge is just one. And covalent bond, you think that the shared pair being attracted by both the nucleus. Certainly, okay, now look carefully, the shared pair being attracted by both the nuclei. Generally we call this covalent bond. But do you think the attraction by this nucleus of hydrogen and this nucleus of chlorine be same? Certainly not. When you think them separately, their separate attractive force are different, and this attractive force, individual attractive force, is called electronegativity. So every atom will have different and individual value of electronegativity. And here we get chlorine will have stronger electronegativity than hydrogen. And when this would happen, then the shared pair will not be in the middle of the nucleus, because that is more attracted by one of the atoms. So the shared pair will move towards one of the atoms. And whenever this happens, you will get the atoms will gain charges. I show the bond here is as a shared pair, that is bond moves towards the chlorine. So chlorine will gain slightly charged, del negative, and this part will be del positive. So these two are poles, forming two poles, positive pole on hydrogen and negative pole on chlorine. And again I say that the charges are not like ionic compounds. Okay, the charges are slight, but they have charges, they gain charges, which means they gain ionic character or ionic properties. This molecule will be affected by charged rod. If you place a charged rod in the sample of hydrogen chloride, charged rod will affect the molecules because they have charges. We call the molecule a polar molecule. This is how a bond, which is actually covalent but gains some ionic properties, and we say the bond is polar now. When this happens, when you get any separate two atoms bond, then certainly they will have different value of electronegativity, and the shared pair of electron will move to the more electronegative atom, and this would cause poles. And if you get a molecule with only one bond, as the bond is polar and the molecule will also be polar. This is how they work. But look, if you get a chlorine bonds with another chlorine, do you think this should be polar? Certainly not, because same atom, same nuclear charge and same size, and altogether they will have same electronegativity. When they have same electronegativity, then the shared pair of electrons supposed to be just in the middle and not move to any of the sides, so not producing poles normally. Another important thing I already have mentioned, that electronegativity, the value of electronegativity depends on two things. One is the nuclear charge and how that affects the value in the periodic table. If you look into the periodic table, when you move from left to the right side across the period on the periodic table, then you, in every step you get one proton increases, okay, from left to right. You get one more proton added to the nucleus of the atom. So left to right, what happens? The electronegativity value will increase. Why? Their nuclear charge increases. And similarly, and at the same time, their size also decreases, because when you get more proton, more nuclear charge in their atoms, then the nucleus, their nuclei will attract the outer electron more. So there will be greater contraction, and this is how their size will decreases from left to right. So this is how, in a period, if you think which element would have the highest value of electronegativity, you will get the rightmost. And the value also changes in the group. If you go down the group, here you also get two things changes. One is the size down the group, size of the atoms increases. The first one, the top one is smallest because the shielding effect or number of electron shell is very small, and on every step you get one more shell. We say this shielding effect increases. So when size increases, then you think that electronegativity value will decrease because the shared pair will go away from nucleus when they make bond. And the other thing, nuclear charge, what would happen to the nuclear charge? The nuclear charge also increases down the group. So these two informations are contradictory. If you know the relation between attraction and charges and sizes, then you can be sure. Look at this, attraction depends on Q1 into Q2, and here I write D square. Here Q1 and Q2 are the charges between which they attract. And what you get down the group, if you apply in a group down the group, nuclear charges increases. So maybe Q1 is increasing, and suppose Q2 be the shared pair of electron, that doesn't change. Okay, so this suggests that attraction would be stronger. That is electronegativity. And how about this D square? This is size. This is radius actually. Size, when size also increases, then that suggests that the attraction decreases. But this matters more. Why? Because here the relation is D square. This is Coulomb's law. Scientist Coulomb has developed this attraction formula. And now you get this D square means that the distance matters more than Q1 alone. So this is why what you would get when you move down the group, the value of electronegativity will decrease. This is how they work. And our scientist Linus Pauling has derived a scale. This is a relative scale. He has given some values. These are relative values of all the elements in the periodic table. You just know the relative trend. From left to right, this value increases, and if you go down the group, the value will decrease. This is the comparative sense. And in different substances will have different amount of poles. I mean, two different substances may not have same amount of poles. Why so? Do you think the pole here in the first molecule and second molecule will be same? Certainly not. Fluorine is much more electronegative than hydrogen compared to chlorine. Chlorine is also electronegative than hydrogen, but chlorine, the below fluorine in the periodic table, so value of electronegativity of fluorine is greater. So this is how the first bond or first molecule will have a stronger dipoles. And if you get the next one, hydrogen with bromine should be less polar. Okay, this is how they work. And then another thing, say, are the polar bond and polar molecule same? When you get a molecule with only one bond, suppose these are the examples, and if the bond is polar, the molecule is certainly polar because that consists of only one bond. If a molecule consists of more than one bonds, and if the bonds are polar, then molecules may not be polar. And I show here for carbon and oxygen bond. Look at this. Do you think the bond should be polar? Yes, because oxygen is more electronegative than carbon. But interesting thing is, if this is carbon dioxide, here is carbon bonded with oxygen, and here just on the opposite side carbon bonds with another oxygen, then what would happen? This time we said the dipoles will be cancelled out. Why this happen? Because here get, when the middle atom is carbon, this bond, the oxygen, here you get oxygen is more electronegative than carbon, then this should be negative and this should be positive. That you get, that you have get here in carbon monoxide. But this is not in carbon dioxide, because same thing happens from the opposite side. Look carefully. If you two person pull a same substance, same thing from opposite side and with the same strength, then what would happen to the object? Would that move to any of the person? No. Here you get two reasons, mention two reasons. One is their strength same, their pulling strength is same. What is the other reason? Other reason is their angle. They are pulling the substance from just opposite side. So the middle thing will be in the middle and will not move to any of the side. So this is how we say that dipoles are cancelled. When these two atoms are same, and when the angles, here you get angles 180 and here you also get 180 on both sides. These two properties together we call symmetric. Symmetric, the word is symmetric, more than same, very same, then we call symmetric. For two conditions, that could be, a shape could be symmetric or molecule could be symmetric. One, when these two atoms or more than two atoms could be same atom, and if you get their bond angles are same, then we say that shape or the molecule is symmetric. And when this happens, symmetric shape, then dipoles will not persist. I mean, the dipoles will cancel each other. And though separately, individually, if you consider this bond, one of the bond, then you think that the bond should be polar. But when you think all the bonds together, then you would get the bonds are not polar, because the polar dipoles cancel each other. And there are many other examples you would get. Suppose carbon tetrachlorides. Here I draw the shape. Shape is very important to understand the symmetric shape. So look at this. This is a symmetric molecule. And individual, this, when you think individual bond, this would be polar because chlorine is more electronegative than carbon. But when you think the total molecule together, then what is there? All four atoms bonded to the central atom, carbon here, are same. And their bond angles are, all bond angles are 1, 0, 9 and 5. And bond angles are same and atoms are same. Together we say that this is symmetric and the dipoles will be cancelled. But if one of the chlorine atom is replaced by another atom, suppose hydrogen, then that won't be symmetric anymore, and that would have slightly poles. Okay, and get here a few more examples, which are, first you get the water, H2O, and water is not like carbon dioxide, which means carbon dioxide is symmetric, but water is not symmetric. Why so? You already got this, the shapes is a V shapes or bend shapes, because here are two lone pair of electrons. Two lone pair of electrons causes the bond angle to be like this, and this you get 104.5. This is the bond angle between two hydrogen atoms. Why is the molecule not symmetric? Here you get 104.5, but this side is big. This side, the other side is big. So this side and the other side is not same. So that won't be a symmetric molecule, and this would be polar. And what would happen here? Oxygen, being more electronegative than hydrogen, will pull electrons from hydrogen, and oxygen will be partially negative, and hydrogen will be partially, both the hydrogen will be partially positive. Water, this is how you get water is a polar molecule. And similarly you get ammonia, and here is a lone pair of electron. Both the bond angle same, 107, and all three atoms are hydrogen, but this is not symmetric because the other side, look at this side, is a big side and will have poles. This is minus, and hydrogen will be positive poles. So this is how they are polar molecules. And when you get the covalent substances like water and ammonia with poles, then they will have stronger intermolecular forces because they have opposite poles, two molecules opposite poles. Then one of the poles of a molecule will attract the opposite pole of adjacent molecule. So there will be stronger electrostatic attraction between opposite poles. This is how they achieve the ionic character. And another thing, when they have poles and strong poles, and they will be water soluble. Ionic compounds are well soluble in water. And ammonia, hydrogen chloride, these are polar, strongly polar molecules, and you will get this ionic properties with them. They are highly soluble in water, and they will also be affected by charged rod, which is also an ionic character.